These are the work solutions to Mechanical Science Sheet 10, Part 1. So the question is, what is the mass of a projectile whose momentum is 200 kilogram meters per second and whose kinetic energy is 2 megajoules? So, sorry, this should say mv is equal to 200. So to start with, we can get our kinetic energy and divide it by mv, and that will give us half v. So we can double this and we can end up with just v. So if we put a 2 here, and then we can erase this and we end up with just v. So that v will be equal to 1 times 10 to the power of 4. So now that we've got v, we can try and work out our mass. So what we can say is mv divided by v is equal to m, and we know mv is equal to 200. So if we divide that by 1 times 10 to the power of 4, we should end up with 1 times 10 to the minus 2. So yeah, that's the solution for the first question. A ball has a kinetic energy of 100 joules. What would the kinetic energy of a ball with twice the mass and half the momentum be? So if we say that we have 100 joules is equal to half v squared, we've got to adjust this to have twice the mass and half the momentum. So we can say our mass becomes 2m, and our momentum is usually mv. But you have to remember our mass is 2m now, so it's going to be 2m, and we'll call this v1 just like so we know what it is. Okay, so if we just go our momentum of value for a second, we could calculate what it is, but let's just say our momentum is equal to 10. If we double our mass, that means we need to half our velocity to keep the momentum the same. So we'd say, okay, that's going to be 2m and v divided by 2. But we actually want half the momentum, so we're going to divide our v again. So instead of v divided by 2, it's going to be v divided by 4. So that way our momentum is going to be like half of what it was before, with using double the mass. Hopefully that makes sense. But the long and short of it is we're going to use this same equation, but now we're going to say half 2m v divided by 4 squared. We can actually sort of rearrange this, so I'll just draw a line here. We can rearrange this, so it's basically half v squared multiplied by 2 multiplied by 1 over 16, because it's 1 over 4 squared, and then we can rearrange it again to be half mv squared multiplied by 1 over 8. And from there you can see that it's going to be our original 100 joules, but divided by 8. So that's 12.5. Sorry, 12.5 joules. A Ferris wheel, like the London Eye, has a diameter of 100 meters. If it rotates so fast that passengers feel weightless at the top of the wheel, what must its angular velocity be, and what then will the ratio between the passenger's kinetic energy and their gravitational potential energy be relative to the ground when they're at the top of the wheel? So first things first, we can equate the forces. So when I say force, I mean mass times acceleration. So we have mass here and we have angular acceleration is equal to acceleration due to gravity and the mass. So if you think about it, these have to be equal for our passengers to feel weightless. So we can cancel out the masses and say omega squared r is equal to g, and then we can rearrange to get omega is equal to square root of g over r, and that's going to be square root of 10 divided by 50, and that's about 0.447 radians per second. So that's the angular velocity, and that's fine. So after that we can say we need the kinetic energy and gravitational potential energy. We can do potential energy first. So that's mass times gravity times height, and we don't know our mass yet, so we'll just say it's a multiple of m. Gravity is 10 and our height is 100 meters, so we'll say m times 1000 is our potential energy, so we'll just call it P. And then our kinetic energy is equal to half mv squared, but we're not using pure velocity this time, we're using angular velocity. So we can replace our velocity with omega r. So that means our kinetic energy equation becomes half m omega squared r squared. So we can actually plug all these values in, apart from the mass, and say from before, square root of 10 over 50 is omega. Since we need omega squared, we're just going to plug 10 over 50 straight in, and our radius is 50 meters, so we can just put 50 squared in there as well, and multiply by mass 2, and we end up with 250 times the mass. So from that we can say the ratio of potential energy to kinetic energy is 1000 to 250, or 4 to 1.